In this video, I will walk through the complete hand-eye calibration workflow using the Zivid Hand-Eye GUI. The goal is to show how to go from a prepared camera and robot setup to a validated and usable hand-eye calibration, following the best practices for accuracy and repeatability. I will use the latest Zivid 3XL250 camera, a universal robot, and the Python-based hand-eye GUI, which interfaces with robotics. The same workflow applies to other Zivid cameras and robot platforms, and I also want to mention that we support 4 degrees of freedom robots. One of the key additions is the session-based workflow, which allows users to organize, save, and reuse data across different steps within the same project. In this case, I start by creating a new session, which will store all captures, robot poses, calibration results, and verification data for this workflow. I am using our latest camera model, as I said, the Zivid 3XL250 at 2.8 meters. The camera is mounted stationary, and the calibration board is directly mounted on the robot arm. This corresponds to an eye-to-hand configuration. When launching the GUI for the first time in a session, a series of configuration windows will guide you through the setup. The first one is the camera selection. Select one of the camera connected. If a firmware upgrade is required, you will be prompted in the next step. Choose the hand-eye calibration tab based on your system configuration, eye-in-hand or eye-to-hand, and then select the calibration object used, either the markers or the calibration board. If you are using markers, define which marker IDs should be detected. Then comes the read-only mode or robot decay, basically how to make move and to read the robot poses. You can select the read-only mode, which does not require a robot decay station, but requires a UR robot. In this case, I'm using robot decay station, which is already configured. I'm gonna explain you later. Then comes the robot rotation format. You can select the rotation representation and unit that match your robot. You can either choose a robot from the predefined list or manually configure the rotation format. All common robot formats are supported. Select the camera settings that will be used for the hand-eye calibration. We recommend using the same settings as in the final application to ensure consistency. We ensure that you are using the same vision engine and the same sampling mode across the whole hand-eye GUI. After the initialization process, whenever you select a functionality in the GUI, such as warm-up here, a step-by-step checklist appears in the top right section. This checklist defines the exact sequence of action and should be followed in your order. Before any calibration, it is important to warm up the camera to ensure optimal accuracy. The warm-up process runs the camera for a specified duration and a capture cycle. During the warm-up, the capture cycle should be as close as possible to the real application. I set the value as if the application captures once every 3 seconds. The warm-up should use the same interval. The camera settings used during the warm-up should also match the application settings as closely as possible. This warm-up method uses the projector as a heating element, and the ratio between projector on time and total cycle time is called the duty cycle, which affects both how fast the camera heats up and the final steady state temperature. Let's move on to in-field correction. In this case, I use robot decay, where a set of robot poses has already been defined. In-field correction is a maintenance tool designed to verify, and if needed, correct and improve the dimension trueness of Zivid cameras. It allows the user to check the accuracy of measurement at multiple locations in the field of view. Dimension trueness refers to systematic measurement errors. It describes how close a measured point is to its true physical position. After the correction, the average dimension trueness error expected is typically below 0.1%. The Zivid cameras are built for industrial environments and maintain high accuracy over time. However, it can occasionally require adjustment due to environmental changes or heavy handling. In-field correction ensures that the camera operates at its optimal performance level. The 2D live view helps to visualize what the camera sees during the process. The GUI also shows when the last correction was applied, if any. Most of applications do not require in-field correction, as Zivid cameras leave the factory already calibrated to the specifications stated in datasheet. I decided to use robot decay with predefined pauses, where the robot iterates through all of these pauses and captures for each of them the calibration board at different distances and across the entire field of view. This is important because in-field correction compensates local dimension trueness error. Once complete, I apply the correction, and the GUI confirms that the camera has been updated, effectively making it extra calibrated. Finally, we can verify the correction by confirming that the dimension trueness error is within acceptable limits. With the camera warmed up and in-field correction applied, we can proceed safely to the hand-eye calibration. I'm using robot decay, where a set of robot poses has already been defined. In this case, the calibration object is now Aruco markers, and I can start the process by clicking the button Auto Run. In this case, the robot automatically iterates through all predefined poses, and the GUI at the same time, for each pose, capture images, record the robot pose, and store all the data in the session directory. At the same time, the 2D live view remains available, and we also have a 2D image for each capture showing the pose of each detected marker. In most of this example, 4 markers are detecting for each capture on the tool. The result from the hand-eye calibration is the hand-eye transformation, which provides the camera pose in the robot base frame. Let's see how to verify the hand-eye calibration. Let's begin with the residuals. During the hand-eye calibration, the camera finds a set of feature points on the calibration board. These are small, repeatable points the software can detect in every capture. After the calibration, all these feature points should line up when transformed into the robot base frame. In reality, they never overlap perfectly, and the differences are called the residuals. Zivid creates an average reference of all of feature point sets and compares each capture to it. The position difference is the translational residual in millimeter, and the orientation difference is the rotational residual in degrees. Smaller residuals mean better calibration. In this case, we expect to have translational residual in the sub-millimeter and having the orientation below 1 degree. We now move on to the projection-based verification, still using Aruco markers. A single capture is performed to detect the markers. After that, when I manually move the robot, the system projects the marker position correctly without performing a new capture. This works because the GUI reads the robot pose, applies the hand-eye transformation, and updates the projected position accordingly. This visual confirmation validates the hand-eye calibration. For the touch test, a robot decay station with a predefined safe waypoint is required. The safe waypoint ensures that the robot transitions safely before approaching the target. In this scene, I place an Aruco marker with ID 5 and I also configure the tool center point length. After capturing the scene and detecting the marker, I initiate the touch operation by clicking on the button. The touch accuracy depends on several factors: the robot calibration accuracy, the hand-eye calibration accuracy, the TCP calibration accuracy, and the calibration object pose estimation accuracy. The GUI allows us to inspect the translational errors along all 3 axes. Touch test verification validates the absolute positioning accuracy, including the TCP calibration. It's important to note that these tools do not replace the robot calibration or the TCP calibration. Instead, we assume that the robot is already properly calibrated and focuses on accurately aligning the camera and robot coordinate system.